What's up, Sim Savages? Sim Science fam, back at it again. Another video. Sim Science Saturdays turn into Sim Science Sunday. We don't stop. We keep going, popping them out left and right. All right, let's keep going. Molecular geometry, okay? So we're continuing to talk about covalent molecules here. All right, we're talking about their different geometries. So let's start with the first question. What does VSEPR stand for? Now, the reason I'm asking this is not so that you memorize what VSEPR stands for, but rather that you get the broad idea of what causes the 3D shapes of different molecules. Okay, so VSEPR, valence, shell, electron, repulsion, hold on, electron pair, repulsion. Okay, valence, shell, electron pair, repulsion. All right, so this is saying that electrons are going to repel each other. That makes sense because they're both negative. Like charges are going to repel each other. So when you have a lone pair of electrons, they're going to repel each other. When you have electrons on different atoms attached to the same central atom, they're going to repel each other. So when we're talking about 3D shapes of molecules, these are determined by electrons repelling each other on atoms and lone pairs of electrons. So what causes the 3D shapes of different molecules? The repulsion of electrons in the molecule. Now, there's a lot of different ways to say that. I didn't make it up, but I just pulled that off the top of my head. Okay, but when you have the ball and stick models that you're drawing, it's always, they want to get as far away from each other as possible. So if you just had three, they're going to spread out so that they have 180 degrees of separation away from each other. Okay, they want to spread out as much as they can. That's why we get these different shapes. And that's what we're going to talk about next, is the different geometries of these different things and why they take them on. Okay, so let's look at the first one here. So I asked you for, in all three of these next upcoming questions, I asked you for the name of the compound, the name of the molecular geometry, and I want you to draw the molecular geometry. Okay, so naming is what we did up here. We're still talking about covalent molecules. Okay, we're still talking about covalent molecules. So BCl3. Okay, so we're starting with boron. Okay, so we know it's going to be boron. And then we have chlorine. We have three chlorines. So it's going to be tri, chlor, not ene though, because it's the second one, it's going to be ide. Okay, boron trichloride. That's what we're working with here. Okay, so we named the compound, boron trichloride. Now we need to figure out the molecular geometry, okay, and the drawing. And you can do these things hand in hand. So we know we have a boron in the middle, right? Let me make this a little thicker. Okay, we know we have a boron in the middle. This is our central atom. And we're going to have three spread out around it. Now there's a few different ways you could approach this, so I think I'm going to try to do it three somewhat different ways throughout this. Let's look at our periodic table down here. Boron is here. Okay, so in the 8 major groups is 1, 2, 3. 3. So it has 3 valence electrons, right? It's group 13 or 3A. As we learn, 3 valence electrons. Okay, and we know it's going to be attached to 3 chlorines, so that works out perfectly. It's going to donate one of each electron to, it's going to donate 1 electron to each chlorine. And we know that chlorine is a halogen, it's over here, so this is in group 8A, I'm sorry, 7A. 7A, it has 7 valence electrons, it just wants 1 more. So it's going to be perfect, it's going to take 1 of each of boron's electrons. Now you might be thinking, but boron's not getting 8 when it does this, and yes, boron is a little bit of an exception to the octet rule. It makes more sense to think of it as boron is giving away 3 of its electrons and getting back to the noble gas before it, kind of like how we look at ionic compounds, because boron is a non-metal, but it's in 3A like aluminum is. Aluminum goes away 3, blah, blah, blah. It's a little bit beyond the scope of what we need to know, but if you were wondering that, that's why. Okay, so we know that boron is going to give 1 electron to each chlorine. It's not going to have a lone pair. There's no lone pair here, so that's important. No lone pair on the central atom. So we just need to worry about these 3 chlorines. They're going to spread out as much as they can, okay? Now, you do need to learn your molecular geometries. So when you hear that there's 3 things on this central atom, and they're going to spread out as much as they can, you don't have to worry about a lone pair. You should know that it's going to be trigonal planar. Trig, 3, Tri, 3, planar. So they're going to spread out as much as they can from each other. So you're going to have a chlorine like this. Each one is going to be spread out as much as they can from each other one. Okay, so that's trigonal planar. This is how it's going to look in general. And we've talked about bent, where if the top, what's on top is a lone pair, it's just going to be bent. But this is trigonal planar. Trigonal planar. Okay, so we confirmed that there wasn't going to be a lone pair, that there were just 3 ligands, there were 3 groups attached to the central atom. If there's 3 groups, they're going to spread out in a trigonal planar way. Okay, let's go on to the next one. All right, so again, we need the name of the compound, we need the geometry, and we need a drawing. Now we're working with PCl5. So let's start with the name. Okay, we know that the first atom is phosphorus. Phosphorus. Now we have chlorine again. Just like up here, we have chlorine again. Now we have 5 of them. 5 of them. So it's going to be phosphorus, penta, that's 5, chloride. Phosphorus pentachloride. Okay? So we're going to have 5 chlorines attached to this central phosphorus. So we have our P here in the middle. Now we need to attach 5. So how many valence electrons does phosphorus have? Here it is. Group 5A. Again, works out pretty conveniently. It's going to have 5 total valence electrons, so it can give 1 to each. So I kept this a little bit simple. You don't have to worry about double bonds or anything like that. So we know that the 5 are going to spread out as much as they can. Okay? So again, if you know your molecular geometries and you know what happens when you have 5 things attached to a central atom, no lone pairs, again, no lone pairs. So we're just worried about the 5 chlorines. This is going to be trigonal bipyramidal. Okay, so it's one of the big ones, one of the big boys. So you're going to have 1 going straight up and 1 coming straight down, bipyramidal. Then you're going to have 3 in the central plane. So let me see. I'm not the best artist. Let's see what I can do here. So you have 1 here. What was that? Why didn't I erase? There you go. Okay, 1 here and 1 here. Now this one here is going backwards. All 3 of these are in a plane like that, and then the 2 are going straight up and down. So this is how they can spread out as much as they can. Trigonal, 3 in the central plane. Bipyramidal, 2 going up and down. And if you want a better depiction of this, you can look at your book. Ooh, off the top of my head, what page? I think it was page 243. Or you can look in your notebook where we talked about this stuff. This is trigonal bipyramidal. So when you have 5 things connected to a central atom with no lone pairs, which I don't think you could have a lone pair with 5 things connected anyway. If you have that, it's going to be trigonal bipyramidal. Okay, so you know your geometries, you know what it is, and hopefully you can depict it somewhat, even if it's as bad as I did. All right, let's go on to the last one. Okay, now we have, again, name, geometry, drawing, CH2. CH2. Okay, so first of all, the name. We have carbon, singular, dihydride. Dihydride. Okay. Oh, wow. Spelled die with a Y. It's kind of embarrassing, but I'm not resheeting this whole thing. Dihydride. Okay. So now carbon we know has 4 valence electrons. It's connected to 2 hydrogens here. Okay. So how many valence electrons are going to be involved in the bonding? 2 for each hydrogen. That means that you still have 2 left on the carbon. So you do have a lone pair. 1 lone pair in this example, okay? So here's our carbon. It's gonna have a lone pair, so we'll just put that up here. And it's gonna be connected to a hydrogen from each of its remaining valence electrons. Okay, so this is what it's gonna look like. All right, so guess what geometry this is gonna be? Bent. Bent, okay? So, including the lone pair of electrons, this is the same as this, trigonal planar. Okay, if you include the lone pair of electrons. But when we're naming it and drawing it as a ball and stick model, we do not include lone pairs of electrons. So just looking at the atoms themselves, it is bent. This is a bent geometry. Okay, so there's some good practice for your geometries, Vesper theory and geometries. So you know that the molecular shape is determined by the repulsion of the electrons in the molecule. That means lone pairs and also electrons on atoms in the molecule, okay? And so when you figure out how many things you have attached to the atom, you can figure out what the geometry is going to be. In an example like this, you could figure out that this has one lone pair and 2 atoms attached to the carbon, so it's going to be trigonal planar, but then you have to realize the lone pair is not included, so it'll be bent. But once you figure out how many things it has attached to it and you know the lone pairs, you can figure out the geometry. All right, so you can use this, and you can use your notebook, the examples we did, you can use your book. I'm sure there's other videos out there, Khan Academy, and everything, wherever you go, YouTube, wherever you want to look, I'm sure you can find more info on this and more practice, and that's what you need to get good at it. All right, so thank you guys for watching. I will put up a video on ionic compounds and naming them soon.